Hello students, welcome to my session. Myself Eswanaja, lecturer in physics from Government Polytechnic Nirmal. Today I am going to explain the phase and the time period of the particle executing simple harmonic motion. First of all, the phase of the particle in SHM. The phase of the particle is nothing but the state of the particle executing simple harmonic motion with regard to its position and direction of the motion at any instant is called the phase of the particle. Means the state of the particle means the position. We can get the knowledge about the position and direction of the motion at any instant of time during the path of the particle is nothing but the phase of the particle. So here observe the slide. The phase constant, it is also called as the phase constant theta 0, theta naught. So the particle is moving in the circular motion, and the phase constant is just an angle. It is just an angle with which the motion started. Means suppose the particle here initially at an angle of theta naught, and it covers a distance, means angular displacement is theta. Initially the position of the particle means at time t is equal to 0 seconds, the particle is at a position means at an angle of theta naught, and during the time t it is shifted to and covers an angular displacement theta. Now the phase constant is nothing but the initial position of the particle. So where is the position of the particle? It is at an angle of theta naught. So this is the phase constant. By knowing this phase constant, we get the knowledge about the position and direction of the motion at any instant of time. So this is the phase constant. Now how to derive the expression for the phase of the particle in SHM. For this I am considering the two figures here. Observe the figure. The first figure, the particle is moving in the circular path x, y, x dash, y dash. Next, the second diagram, also the particle is moving in x, y, x dash, y dash. What is the difference between these 2 points? These two figures means, in the first figure, the particle is initially at a position, and it is in time t seconds it is shifted to p point. And in the next figure, the particle initially at point B, and it shifted to p point during the t seconds. So the first for the first figure I am considering the phase. What is the phase and what is the expression for displacement of the particle executing SHM. So to get the value of the displacement, first of all, what is the position of the particle initially at time t is equal to 0. So in the first figure, the particle is at a point, means it is making angle phi naught with respect to x axis, that is x dash. It is a horizontal diameter. Next it makes an angle phi naught at time t is equal to 0 seconds. So that is the position of the particle. Then in time t seconds, so it covers, it shifted to point P. It is shifted to point P. Means with respect to angular, means horizontal axis, that is x dash, the total displacement is omega t. The total displacement is omega t, and with respect to horizontal axis, the displacement is t phi. The displacement is phi, means with respect to horizontal axis, the initial position is at an angle of phi naught, and during the time t seconds it is shifted to point P, and the point P is at an angle of phi. The initial position is at an angle of phi naught. The final position of the particle is at an angle of phi. Then the total displacement, the total angular displacement is nothing but phi plus phi naught. So this is we have to consider as omega t. Phi plus phi naught is equal to omega t. Now the total, if the particle passes from the position A to P, then y is equal to r sin omega t minus phi naught. Omega t minus phi naught means the particle is at P with respect to x-axis. The angular displacement is phi. So phi can be written as omega t minus phi naught. Omega t minus phi naught. So the displacement of the particle is y is equal to r sin omega t minus phi naught. When t is equal to 0, the y is equal to r sin phi naught. Y is equal to r sin phi naught. Next, from the figure B, next figure, the particle is initially at a point B and it is shifted to B. Means the particle passes from X to P position. No. It is from B to P position. So y is equal to r sin omega t plus phi. Means the particle is at a B point. So the initial the displacement is phi naught, and during the time t seconds it is shifted to P point. So the angular displacement is omega t. So the total displacement is equal to omega t plus phi naught. Omega t plus phi naught. So y is equal to r sin omega t plus phi naught is the displacement of the particle executing SHM. Now when t is equal to 0, then y is equal to r sin phi naught. So here phi naught is the initial phase or phase constant. Initial phase or phase constant of the particle executing SHM. So in both cases, the initial position of the particle is at A, and in the second figure it is at B point. So with respect to x dash horizontal diameter, the phase constant is phi naught in both cases, but the total displacement is equal to y is equal to r sin omega t minus phi naught, and in the second case y is equal to r sin omega t plus phi naught. Now, in one oscillation, radius vector sweeps 2 pi radian. In one oscillation, the radius vector sweeps 2 pi radian. If the angle swept in time t seconds is phi, then for one complete rotation of the radius vector, the foot of the perpendicular execute one complete oscillation. So the radius vector makes complete 2 pi radians in one oscillation, means in one rotation, and for the for one complete rotation of the radius vector, the foot of the perpendicular execute one complete oscillation. So omega is equal to phi by t. phi by t. For one complete rotation, phi is equal to 2 pi. So we know that omega is equal to 2 pi by t is equal to phi by t. Then phi is equal to 2 pi by t into small t radian. So this is the phase of the particle executing SHM. So in radians it is 2 pi t by capital T. What is phi here? Phase of the particle. Small t is the time. Capital T is the time period. Small t is the time for one oscillation. So here phi is equal to 2 pi t by capital T radians, or 360 into small t by capital T. This is in degrees. So see the slide. So the initial position is P and shifted to another point P. So the total angular displacement is omega t. So reference point is P here. So for one rotation it is oscillating to and fro motion along the vertical diameter. Ideal simple pendulum. What is meant by ideal simple pendulum? So it is defined as heavy point mass suspended from a rigid support by means of weightless and inextensible string and set of oscillating under gravity through a small angle in a vertical plane. So here the ideal simple pendulum has some unique features here. First of all, a heavy point mass should be suspended from a rigid support. The bob will be heavy point mass and it must be suspended from a rigid support, and it is suspended by a rigid support by means of what? It is a weightless inextensible string. Weightless inextensible string and set of oscillating under gravity through a small angle. It is oscillating in a vertical plane through a small angle theta. So see here in this slide you can see the ideal simple pendulum. So that has the features: the massive bob. The bob will be massive bob, and the rigid support, it is a frictionless pivot, and the rod is massless rod. Massless rod or massless string. And observe the bob's trajectory. It is a parabola and it is moving the small angle theta, and there will be shown in the figure the equilibrium position of the bob also. And the maximum displacement is nothing but the amplitude of the simple pendulum. So this is the ideal case. A heavy point mass suspended from a rigid support by means of weightless inextensible string and makes oscillations in the vertical plane through a small angle theta. Now, what is the time period for the simple pendulum? What is the time period? It is the time for one oscillation. We already calculated the time period for a particle in SHM. T is equal to 2 pi by omega. So here, to get the expression for time period of simple pendulum, I am considering the bob during its vibratory motion as shown in this figure. So the bob is in the equilibrium position and it is moved at an angle theta, and it goes to the extreme position and coming towards the equilibrium position, then another extreme position. Like this, it is making oscillations in the vertical plane. So it is in the oscillatory motion. The metallic bob is in the oscillatory motion as shown in this figure, and the mass of the bob is small m. We are neglecting the mass of the string or the thread. Now x be the displacement of the bob from the mean position. What is the mean position here? It is A, and the extreme position of the bob is B, and AB is the maximum displacement, so that is x. The maximum displacement is nothing but it is the amplitude of the simple pendulum. Now in the simple pendulum, there are two forces are acting on the bob at this position. For the simple pendulum, so two forces are acting on the simple pendulum. If you observe the simple pendulum at the mean position or it is at the extreme position. First of all, if the particle is in the mean position, means in the equilibrium position, what are the forces acting on the metallic bob? The first force is the weight of the bob. What is the weight of the bob? The mass of the bob is small m, and the weight of the bob is mg. The weight mg is acting vertically downwards. Then the tension in the string is acting towards the rigid support along the direction of the string. The tension in the string is along the string and it is acting towards the rigid support, whereas the gravitational force, means the weight of the body, is acting in downward direction. So here these two forces are balanced each other, means the weight is balanced by the tension in the string in the mean or equilibrium position. Whereas when the particle is at the extreme position, the weight mg is acting again towards the downward direction, and it can be resolved into two components, the two rectangular components. The two rectangular components are mg cos theta and mg sin theta. The mg cos theta is acting along the string. The component of the weight mg cos theta is along the string, whereas the component of the weight mg, that is mg sin theta, is perpendicular to the string. Along the string is mg cos theta and the perpendicular to the string is mg sin theta. There are two components. Observe the slide here. Weight of the body, the bob is mg acting towards the downward direction at B point. Mg cos theta is along the string and mg sin theta is perpendicular to the string. Now, as there is no motion of the bob in the direction of the string, we know that there is no motion of the bob in the direction of the string. The component mg cos theta balance the tension in the string. So, the tension in the string is balanced by the weight of the body mg at the equilibrium position, whereas the tension in the string, that capital T, is balanced by mg cos theta at the extreme position. The mg cos theta is balanced by mg means mg cos theta is balanced by the tension in the string at the extreme position. And there is no effect of, means there is no motion of the bob in the direction of the string. The motion exists always perpendicular to the string. So At is equal to mg cos theta. So these two cancel each other. Okay. Then the component mg sin theta is responsible for the motion of the bob. mg sin theta is the responsible for the motion of the bob, and which brings the bob back towards the mean position. mg sin theta is responsible for the motion of the bob and it brings back to its mean position. Means this will be like the restoring force. mg sin theta acts like restoring force. The force which brings the body to its original position. Restoring force. So, F, the restoring force, is equal to mg sin theta. So, it is always opposite to the motion of the body. So, that's why it is minus mg sin theta. So, if A is the acceleration of the bob at point B, and according to Newton's second law of motion, what we can say that the force is equal to ma. The force is equal to ma. So, by comparing these two equations, F is equal to ma and F is equal to mg sin theta. What is the acceleration of the particle? Means what is the acceleration of the bob here? A is equal to g sin theta. Just I am comparing these two equations. First is mg sin theta, restoring force F is equal to mg sin theta, and the next one, force is equal to ma. So, acceleration simply equal to A is equal to g sin theta. As we know that according to trigonometry, if theta is small, then sin theta is also very small. Sin theta is very small, it is nothing but equal to theta. Sin theta is approximately equal to theta when theta is small. So, therefore, we can say that acceleration of the particle A is equal to minus g theta. A is equal to minus g theta. Now, when theta is small, the S, that is arc length. What is the arc here? AB is the arc. That is equal to x. Means the displacement of the particle is x and the length of the bob, that is OA, is equal to L. L is the length of the pendulum and the arc length is x. and we are considering that theta is very small. Now by applying the trigonometric ratio, tan theta is equal to opposite by adjacent. The opposite is, that is AB, and adjacent is OA. AB is equal to X and OA is equal to L. So theta is equal to AB by L, that is X by L. Means for small values of theta, sin theta is equal to theta and also tan theta is equal to theta. So therefore we get theta is equal to X by L. From the, if we imagine a triangle, that is OAB is a triangle, right angle triangle. So A is equal to minus g theta. We got the equation in previously, A is equal to g theta. Now substitute theta value, that is X by L, in the equation. So A is equal to minus g into X by L, minus g into X by L is the acceleration of the particle. Now here g is the constant, that is 9.8 meter per second square, and L is the length of the pendulum, that is also constant. And here since g by L is constant, we get an equation like acceleration is equal to minus some constant, that is g by L, into X, minus constant into X. So what is X here? Displacement. A is the acceleration. So we got an equation like A proportional to minus X. A proportional to minus X. Means acceleration is proportional to displacement, but acceleration, the direction of acceleration is opposite to the direction of displacement. So this relation we already discussed in the conditions of SHM. The conditions of in SHM. Acceleration is proportional to displacement and opposite to displacement. So this equation A proportional to minus X shows that the acceleration of the bob is directly proportional to the displacement X, and negative sign shows that it is directed towards the mean position, and hence the motion of the simple pendulum is simple harmonic. So the simple pendulum, the motion of the simple pendulum, clearly we can say that it is simple harmonic, A proportional to minus X. And we got a relation, that is A is equal to minus gx by L. Then the time period of simple pendulum. How to get the value of simple pendulum's time period? So the acceleration of the particle, we got an equation that A is equal to minus omega square x. A is equal to minus omega square x. And here the acceleration of the simple pendulum is A is equal to minus g x by L, minus g x by L. The first equation is A is equal to minus omega square x, and the second equation is A is equal to minus g by L into x. So by comparing these two equations, we get an equation that just equate these two equations. The minus omega square x is equal to minus gx by L. So x get cancelled. Omega square minus minus also get cancelled. Omega square is equal to G by L. We got omega square is equal to G by L. So omega is equal to under root of G by L. What is G here? Acceleration due to gravity. L is the length of the pendulum and omega is angular velocity. Omega is equal to under root of G by L. So we got the formula, that is omega is equal to under root of G by L. But we need the equation for time period. Then what is the relation between the time period and omega? That is T is equal to 2 pi by omega. T is equal to 2 pi by omega, where omega is under root of G by L. So time period T is equal to 2 pi by omega is under root of G by L. So T is equal to 2 pi under root of L by G. 2 pi under root of L by G. T is the time period, L is the length of the pendulum, and G is the acceleration due to gravity. So T is equal to 2 pi under root of L by G is the time period of the simple pendulum. It is in simple harmonic motion. So from this equation, the time period T is directly proportional to root L and inversely proportional to root G. T is equal to 2 pi under root of L by G. Now the laws of pendulum. The laws of pendulum. So we have 4 laws. The law of length, the law of acceleration, the law of mass, and the law of amplitude. The first one is the law of length. The time period of simple pendulum varies directly as the square root of the length. Square root of the length means the time period T is directly proportional to square root of the length of the pendulum. T proportional to root L. T proportional to root L. And means by increasing the length of the pendulum, the time period of the pendulum increases. And by decreasing the length of the pendulum, the time period means the time for one oscillation is also decreases. That is the meaning of the first equation, the law of length. Then the law of acceleration. The law of acceleration. The time period of simple pendulum varies inversely proportional to the square root of acceleration due to gravity. So it is inversely proportional to square root of the acceleration due to gravity. Means if we compare the acceleration due to gravities at different planets, means at the Mars, at Earth, at some Jupiter, like different planets, the G value will be different at different places. Means then the time period of the simple pendulum at these different places also changes. According to the equation, T is inversely proportional to root G. Means by increasing the G value, the time period decreases. By decreasing G value, the time period increases. So this is the law of acceleration. Then we go for the law of mass. Law of mass. The law of mass. The time period of simple pendulum is independent of the mass and material of the bob. So if we consider one bob and we calculated the time period of the simple pendulum, and if we change the material of the bob or the mass of the bob, means whether if we change the size of the metallic bob also, means we are not changing the length and we are not changing the position of the particle, means the position where we are doing this experiment. So by changing the size of the metallic bob or by changing the size and the nature, the material of the bob, means suppose it is metallic bob or bronze or any silver, like if we iron, if we consider different types of material of the bobs, then for a fixed length of the bob the time period is always same, means it is independent of the size of the bob and it is independent of the material of the bob. It simply depends on the length of the bob and acceleration due to gravity. And finally, the law of amplitude. What is meant by amplitude? The maximum displacement is the amplitude. So the time period of the simple pendulum is independent of the amplitude provided. The time period of simple pendulum is independent of the amplitude provided, means the amplitude should be small for the simple pendulum, means to eliminate the errors. Actually, to by doing the experiment, the time period of simple pendulum, we have to maintain that the amplitude of the simple pendulum should be small. Why? Because if the amplitude is very large, instead of oscillatory motion, the bob will be spins. The bob will be the spinning motion of the particle. So then we can get the errors also. So to remove these errors, we have to follow that the amplitude of the simple pendulum should be very small. And if we change the amplitude, this amplitude for there is a slight variation in the amplitude, then also there will be no change in the time period of the simple pendulum. So that's why we can say that it is independent of amplitude. So according to the laws of pendulum, it is directly proportional to the square root of the length of the pendulum, and it is inversely proportional to square root of the acceleration due to gravity. The time period is independent of the mass of the bob and it is independent of the material of the bob. And finally, the time period is independent of the amplitude also. So these are the laws of pendulum. Now we go for the final concept, that is seconds pendulum. The seconds pendulum. What is meant by the seconds pendulum? It is a pendulum whose time period is 2 seconds. Whose time period is 2 seconds. The simple pendulum whose time period is 2 seconds is called seconds pendulum, means it takes 2 seconds for one complete oscillation. It takes 2 seconds for one oscillation. Then what will be the length of the seconds pendulum? For which length of the pendulum the time period will be 2 seconds. To get that value, so first of all, what is the time period of the simple pendulum? T is equal to 2 pi under root of L by G, where L is the length of the pendulum, T is the time period, G is the acceleration due to gravity. So here I am just simply squaring on both sides. T square is equal to 4 pi square L by G, means the square root of L by G whole square will get L by G. So T square is equal to 4 pi square L by G. So we know that T is equal to 2 seconds. Length we don't know, and g is equal to 9.8 meter per second square. Or here we can simply take it as 10 meter per second square. So if we substitute 9.8 meter per second square or 10, simply approximate values, some 10 meter per second square is substituting here to get the value of the length of the seconds pendulum. So L is equal to g t square or t square g by 4 pi square. So t square means it is 2 square into 10 by 4 into 3.14 whole square. So 40 by 39.43. So it is equal to 1.01 meter, means approximately 1 meter, 100 centimeters. So the length of the seconds pendulum is approximately 1 meter. So if we construct a pendulum of 1 meter length, then for a given the acceleration due to gravity 9.8 meter per second square, we get the time period is equal to 2 seconds. Means if we calculate the time for one oscillation, we get 2 seconds. So if we substitute 9.8 meter per second square, then we get the value approximately 0.99 something meters. So here we are taking as 10 meter per second square. So we are getting 1.01 meter here. So this is the seconds pendulum. So here in the session we discussed the phase and time period of the seconds pendulum. The phase of the particle is the state of the particle executing SHM with regard to its position and direction of the motion at any instant of time is called the phase of the particle. Means it tells about the initial position of the particle at any instant of time. So here we are getting the two we discussed two different cases. Then y is equal to a sin, means r sin omega t minus phi naught, or y is equal to r sin omega t plus phi naught. So here phi naught is the phase constant or phase of the particle in SHM. Now for one oscillation the radius vector covers 2 pi radians. So omega is equal to phi by t. So 2 pi by t is equal to phi by t. Then phi is equal to 2 pi t by capital T radians, or 360 into small t by capital T degrees. So this is the phase of the particle. Then the ideal simple pendulum is the heavy point mass suspended from the rigid support by means of weightless and inextensible string and set the oscillatory under gravity through a small angle in the vertical plane. So this is the ideal simple pendulum. And here we calculate the time period for simple pendulum. So for that I am considering the simple pendulum and it is making oscillations in the vertical plane. So A is the mean position and B is the extreme position, and at a mean position the tension in the string is balanced by the weight of the body, the means weight of the bob, mg balanced by T. So both are cancel each other. Whereas in the extreme position the tension in the string is balanced by mg cos theta, means mg, there is no motion along the string, it is perpendicular to the string. So mg cos theta is balanced by the tension at the extreme position, whereas mg sin theta, the perpendicular component of the weight, is acts like a restoring force, means that this force is brings back to the its original position, means its mean position. So it brings the bob into its original position, means it acts like the restoring force. So F is equal to mg sine theta, and we know that according to Newton's laws of force, F is equal to ma. So simply acceleration is equal to g sine theta, and for very small angle of initial amplitude, theta is small, and for the very small values of theta, sin theta or tan theta is approximately equal to theta. So A is equal to minus g theta is the equation, and we are getting the value of theta, means by using the tan theta it is equal to x by L, and theta is equal to x by L. So F is equal to, means acceleration is equal to minus g x by L is the acceleration of the particle, means the bob. So here I is equal to, we already get the formula like A is equal to omega square x. So omega square x a acceleration, and A is equal to minus g x by L is the equation. By comparing these two equations, omega square is equal to g by L, and omega is equal to under root of g by L, and time period of the pendulum is 2 pi under root of L by g, where L is the length, g is the acceleration due to gravity, and t is the time period of the simple pendulum. And finally, we discussed that the loss of pendulum is proportional to, the time period is directly proportional to the root L and inversely proportional to root G. It is independent of the mass, and it is independent of the size of the bob, and finally it is independent of the amplitude also. And second pendulum is the pendulum which whose time period is equal to 2 seconds is called seconds pendulum, and the length of the seconds pendulum is approximately 1 meter. So this completes my session. Thank you one and all.